Namaste. Hearty welcome everybody. Myself, Mrs. Rosen Jacob, PGT Physics from JNB Pathanamthitta. Here I am to deal with the magnetism and matter of class 12th. So, here we will deal with magnetism and matter today. Let us today begin with an activity. Let's watch it.
Hello dear children, welcome to my class on magnetism. Here there is a magnet and there are some substances placed here. This is silver, gold and copper. Now I am moving this magnet near this silver. So it is not at all attracting. Then to gold, no attraction. Then to copper, it is not at all attracting it. Now I am moving the magnet onto this iron filings. You can see that the iron filings are get attracted to the magnet. Can you see it? So this is a property of magnet. It attracts iron filings. Now I am moving this magnet towards the steel scissor and you can see the scissors got attracted to the magnet. The steel is attracted by a magnet. Likewise, these pins got attracted to the magnet. So, this difference between these materials is due to their difference in the property of electrons. And here you can see an iron rod and a copper wire is wound over it. It is connected to a battery. The circuit is not complete, and when this iron rod is placed near this steel pin, I am moving this near to it. You can see that there is no effect on the pin for this iron rod. Now, when the circuit is completed, and this iron rod is moved near to the steel pin, you can see that the pin is getting attracted to this rod. Current is passed through this coil. There is magnetic field along the axis of this coil and the iron rod inserted in this gets magnetized. That is why it is getting attracted to the pins. This rod is getting magnetic property. Hello, dear.
So, that was activity on magnetism. So, that was an introductory activity. And in this world, we are familiar with magnets. They are used everywhere. We are very familiar with those one rule used in the doors of our refrigerator. It is getting closed automatically. So it helps to save energy, electric energy. So these magnets come in different sizes, shapes, materials, and strength. They have put a wide variety of applications in our daily life, like loudspeakers, vehicles, smart cards, phones, MRI scanning machines, etc. Okay, we are well aware of these uses, and today we will deal with these topics here. The bar magnet and magnetic field lines. Bar magnet equivalent to a solenoid. Torque on dipole in magnetic field. Magnetism and Gauss law. Earth's magnetism. Diamagnetic, paramagnetic and ferromagnetic that will come in the next lesson. Permanent magnets and electromagnets. These will be dealt in the next lesson but in the same chapter. Let's move on to the first topic, the bar magnet and its properties. So, as you are aware, this bar magnet is a piece of metal or alloys made up of iron. So it has the magnetic property. It has two poles, north and south poles. Here you can see two bar magnets attracting and repelling each other. Okay. So the length of the magnet is denoted by length 2L. It is known as the magnetic length. And the pole, they have the same strength when you are cutting a magnet into two halves, you can see that it will become, so this magnet will become two magnets. There one pole is here, another pole comes here, south, here there will be north pole, here there will be south pole. You will get two magnets. Whenever you are cutting this magnet into smaller pieces, you will get more and more magnets, but always there will be north and south pole. You cannot separate two magnetic poles. That is why it is termed as a magnetic dipole. And you know the property of magnet. When it is freely suspended, this will align along the north-south direction. The end which is sticking towards the north is known as the north pole. Why it is getting aligned along this direction? Because you are familiar that unlike poles attract, therefore naturally it will be attracted to a south pole. South pole of which magnet? Oh, our own planet, the Earth. It is a giant planet, giant magnet. Okay, so Earth also has got magnetic properties, and the north pole of the magnet is attracted to the south pole of the Earth magnet. That is why a freely suspended magnetic dipole is aligned along the north-south direction. And here you can see attraction of opposite poles and repulsion of like poles. Now we were dealing with bar magnet and properties. You can see magnetic field lines. These are magnetic field lines. They are coming out of the north pole, then move as loops. It is entering in the south pole. It is continuing and it is coming here. So they will form closed loop. This is the property of magnetic field lines. They form closed loops. And here also you can see that the magnetic field lines will never touch each other. Here it is not ending here, it is continuing as closed loop only. Okay, so these two field lines will not cross each other because at the point of intersection, the magnetic field will point in two directions. A compass needle cannot point in two directions at a single point. Hence, two magnetic field lines will not intersect. These are the two important properties of magnetic field lines. And as we have said, both the poles have the same strength. It is known as pole strength denoted by small m. Its SI unit is ampere meter. And the dipole moment is another quantity which is the product of magnetic length 12 and pole strength m. Its SI unit is ampere meter square. Now, the force of attraction or repulsion between two magnetic poles is directly proportional to the product of their pole strengths. If pole strengths are denoted as M1 and M2, you can write it as F proportional to M1 into M2. And this force is inversely proportional to the square of distance between them. That is F proportional to 1 by R square. And combining this, you can write it as F proportional to M1 M2 by R square, or F equals K M1 M2 by R square. This equation, this constant K equals mu 0 divided by 4 pi, where mu 0 is the permeability of vacuum, which has a value 4 pi into 10 raised to minus 7 Tesla meter per ampere. Now, the magnetic field, we are coming to the magnetic field. Here you can see a bar magnet and iron filings are attached to some specific lines. These lines, so here also you can see these iron filings are arranged in a particular pattern. So this pattern represents the magnetic field around this magnet. That is, if you are bringing any another magnet into this field or any other material which can be attracted by magnets, they will experience the force. If you are bringing a current carrying conductor also, it will experience a force of attraction or repulsion. So this region around a magnet in which another magnet or a current carrying conductor or a moving charge experiences a force is known as the magnetic field of this magnet. And here also you can see the magnetic field associated with the current carrying coil. And here you can see magnetic field lines. Their distances are different everywhere, so it is a non-uniform. So magnetic field are of two types: uniform and non-uniform. First of all, we will with the uniform magnetic field. In this diagram, you can see that equidistant dots. This represents a magnetic field lines coming towards you. If you are looking onto which, the magnetic field lines will be coming towards this. Here, the magnetic field lines are equidistant and parallel. This also represents a uniform magnetic field. It is directed from left to right. Here, you can see equidistant cross marks. It is a magnetic field entering into the plane of the diagram. So all these here also it is a magnetic field from left to right. This is from down upwards and this is towards the left. All these represents uniform magnetic field where the strength of the field is same everywhere. But in this diagram you can see non-uniform magnetic field associated with the bar magnet and a current carrying solenoid where the strength of the field are different at different points. You can see that strength is more at the poles and it is very feeble at the middle part or equatorial part. So where the strength of the magnet is maximum, that point is known as the pole of the magnet. Okay. Now we are going on to the derivation of magnetic field due to a dipole on its axial line. Dipole means a bar magnet because it consists of two poles, two magnetic poles. Here in this diagram, you can see a bar magnet of length 12 with the central point O. Then this is the axial line which is connecting the north and the south pole line passing through the north and south poles. There is a point P at a distance R from the center of the dipole. We want to calculate the intensity of magnetic field at this point P. For that, we are placing a unit north pole here. So this north pole here, you have north pole. This north pole repels with the maximum force and this south pole attracting it with the minimum force because due to the larger distance, therefore net force will be along this direction. That is intensity of magnetic field at this point B. P will be directed from left to right. And the dipole moment of the magnet also directs from south to north. So this dipole moment and B, intensity of magnetic field, they are acting along the same direction. Now applying Coulomb's law here, we can derive this expression and finally reach mu 0 divided by 4 pi into 2mr divided by r square minus l square the whole square. And we are approximating if the distance is the distance to the point is very much greater than the magnetic length, this L can be neglected. Therefore, in the denominator, you will get r raised to 4. 1 r will be cancelled. You will get b is equal to mu 0 by 4 pi into 2m by r cube. This is the required expression. It acts along the direction of m. Now, we are moving on to the axial field of a solenoid. Solenoid, as you know, you have studied it in 10th class, that it consists of a copper wire wound in the form of very close loops in the form of a cylinder over a core. Okay. Now a section of this is shown of thickness dx and the number of turns per unit length is n. What is number of turns per unit length? The number of turns present in 1 meter length of. If it is 1 meter, the number of turns here will be denoted as small n. That is known as number of turns per unit length. Okay. Now, this section is of thickness dx. Therefore, the number of turns present here is small n into dx. Okay. So, this element is at a distance x from the center and our point, the point for finding the magnetic field intensity is P, which is at a distance r from the center of solenoid and current passing is I. Okay. So, this has a radius r. Now, the area of cross section will be pi r square. Okay. Now, we will be calculating the intensity of magnetic field at this point B due to this section of this solenoid. That is, we will divide this entire solenoid into small sections of equal thickness dx. Find the intensity at P due to all these elements as dB. Then we will add together to find the total intensity, and that process is known as integration. Now we obtained this expression, the intensity at P produced by the current through this section of the coil is given by dB is equal to mu 0 n dx I a square divided by 2 into r minus x whole square plus a square raised to 3 by 2. And on integrating from negative L to positive L, total length is 2L. This point is 0. So, this point is at negative L and this point is at a positive L distance. So, if you are taking the total distance from negative L to positive L, you will get 2L. Okay. Now, on integrating this expression from negative L to positive L, we will get the final expression and approximating R very much greater than L. That is, this point is very much far away from this solenoid. You will get the final expression as B is equal to mu 0 divided by 4 pi into 2m by R cube. So we have seen earlier that the actual field of bar magnet, it is the same as this one. So we can say that bar magnet and a current carrying solenoid are equivalent. And the magnetic dipole moment of bar magnet is 2L into M. What is the magnetic moment of a current carrying coil? It is given by M is equal to N into IA, where N is the total number of turns, I current passing through the coil, and A is the cross-sectional area of the coil. Okay. Now, look at this coil. Here, current is flowing in the anti-clockwise direction. So, the magnetic field produced in this coil and this face of coil will be presenting a north pole for an observer. If you are looking from here, you can see a north pole here. If you are placing a magnetic north pole here, it will be repelling this coil. Okay. And that is denoted by the magnetic field here as a dot. That is, magnetic field lines are coming towards you. Magnetic field lines emerge from the north pole. That is why it is denoted by a dot here. And here current is in the clockwise direction as observed here. So it will present a south pole and the magnetic field lines will be going away from you. Okay. Now we will learn the field due to dipole on the equatorial line. That is, here The magnetic dipole with the length 12 is shown here. This is the axial line with the midpoint O. Now, the perpendicular plane to this axial line is known as the equatorial plane, and P is a point on the equatorial plane at a distance d from the center. Okay. Now, for calculating the intensity of magnetic field here, what you have to do? You should place a unit north pole there and find out the intensity and vectorially add. So, you will get the intensity of magnetic field. So, here north pole is there. It will be repelling along this direction, and south pole will be attracting. So, by applying parallelogram law of vector addition, you can draw parallelogram, or it can be resolved into two components. The diagonal of parallelogram will be denoting the resultant intensity along this direction. Now, at this point, you have two vectors B1 and B2. B1 is resolved into perpendicular component B1 sin theta upwards, B1 cos theta towards the left. Then B2 is resolved as B2 sin theta downwards, B2 cos theta leftwards. These being equal and opposite cancel each other, and this being in the same direction, they will add up. Okay, we can add these and we will get this expression mu 0 m by 4 pi into d square plus n square raised to 3 by 2. And by approximating, that is, this distance is very much greater than the length of the magnet, we will arrive at this expression mu 0 by 4 pi into m by dq. What is the difference of this expression from the previous one? That one axial. You can see a difference in the numerator. In that expression, you have got mu 0 into 2 up. Okay. So that is the only difference. And there is one in magnitude. But what about the direction? The axial field was along the direction of M. Okay. And now look here. Here is the south pole. The magnetic moment is directed from south to north. Isn't it? Now we have got the intensity of magnetic field along this direction. What is the relation between their directions? Okay. They are opposite. So here on the equatorial plane, the magnetic field is opposite to that of the dipole moment. Okay. Now we are moving on to the next topic, that is torque on dipole in uniform magnetic field. Here a uniform magnetic field is shown between two magnetic pole pieces. This is represented by equidistant parallel lines directed along a single direction, and a magnetic dipole with a magnetic pole strength M and length 12 is aligned with its magnetic moment vector directed from south to north at an angle theta with the external magnetic field. This field exerts a force on this pole as F is equal to M into B. Same force will be acting on the opposite, but in the opposite direction. So the net force on the system is 0 and it produces no translatory motion. The magnet will not move from one place to another. Instead of that, it will rotate due to a couple. Why couple is formed here? The lines of action of these forces are not coinciding. If they were coinciding, that will cancel. Okay. But as the lines of action of these anti-parallel forces are not coinciding, these two anti-parallel forces will form a couple. And it will try to rotate the magnet in this magnetic field. And the torque for this rotation can be calculated as one of the forces into perpendicular distance between their lines of action. Perpendicular, this is one line of action, this is one line of action, and this is the perpendicular distance. Okay. Now, this distance is 12, this angle is theta. So, this side is 12 cos theta and this side will be 2L sine theta. Therefore, MB into 2L sine theta will give you the torque. That is the magnitude of torque. So is equal to MB sine theta, and direction will be perpendicular to the plane containing vector M and vector V. It is a vector. So its direction is given by the product of cross product. Okay, by the direction of cross product. Now, when this magnet is rotating in this magnetic field, it is disturbed and it will undergo oscillation. And the time period of oscillation is given by T is equal to 2 pi into square root of I divided by MB, where I is the moment of inertia of the magnet about the axis of rotation, and I is equal to ML square divided by 12 for a rectangular rod rotating about its axis of rotation, passing through the center and perpendicular to the larger surface. You have studied it in 11th class. Moment of inertia, its expression is given by ml square by 12, where m is the mass and l is the length of the rod. Okay, so that should be applied here. You will get the time period of oscillation of this rotation. Now, when the magnet is rotated in the magnetic field, it will store energy. That stored form of energy is known as the potential energy. And the work done in rotating the field is stored as the potential energy, and its expression is negative m into b cos theta or negative m dot b in vector notation. Even if it is vector notation, it is not a vector, as it is a dot product or scalar product. Okay, so it is a scalar quantity. Energy is a scalar quantity, work is a scalar quantity. And when theta is 0 degree, that is when the magnet is aligned its moment parallel to the external field, at that position, u is equal to mb into cos 0. Cos 0 is 1. Okay, so u is equal to negative m into b, which denotes the minimum potential energy stage. That is the stable equilibrium. So, what is stable equilibrium? If you are disturbing the magnet a little, it will just come back to its same position very quickly. That is the stable equilibrium position. Its angle will be decreased only. Okay. But in the case when theta is 180 degree, that is its moment is aligned opposite to the external field, u is equal to positive mb, because cos 180 degree is negative 1. So potential energy become positive and the system is unstable equilibrium. Unstable equilibrium means that if at that position, if we are disturbing the magnet a little bit, its angle will become increasing and it will be going to the stable equilibrium position. It will oscillate a little bit due to inertia of motion. Then it will come to rest in the position of stable equilibrium. So that is the position of unstable equilibrium. Got the point? Now we are moving on to Earth's magnetism. You know that Earth's magnetism, Earth has a north pole and a magnetic north and south pole, and it is due to the convection current in the outer core of the Earth. You are familiar with the structure of Earth, so its inside is very hot, and there will be ions. So along with the rotation of the Earth, this rotation of the ions also produces current, which will be the reason of magnetism of Earth. And we have to study two terms associated with the Earth's magnetism, that is magnetic meridian. That is the vertical plane passing through the magnetic axis. Magnetic axis means the straight line connecting the magnetic north pole and the magnetic south pole. This axis, if you are cutting the earth into two halves, along a vertical plane. That plane is known as the magnetic meridian, and there will be a geographic meridian connecting the geographic north and south poles. If you are cutting the earth into two halves along a vertical plane, that vertical plane is known as the geographic meridian. Okay. Now we will move on to the elements of Earth's magnetism. First one is magnetic declination, which is the angle between the geographic meridian and the magnetic meridian. So this smaller angle between the geographic meridian and the magnetic meridian is known as the magnetic declination, denoted by theta. Now there is another angle that is also known as dip angle or magnetic inclination. Dip angle or magnetic inclination. It is the smaller angle between the magnetic axis and the horizontal. So there is the smaller angle between the magnetic axis. This is the magnetic axis and this is the horizontal. This angle delta is known as the angle of dip. Now you can see here that the Earth's magnetic field is directed along this direction. So its vertical component is this one denoted by V and its horizontal component is denoted by H. Therefore, B is equal to B sine delta and H is equal to B cos delta, and their ratio is known as tan delta. This is the relation between vertical and horizontal components where delta is the angle of dip. And angle of dip will have different values as you move from one place to another on the Earth's surface. So it will angle of dip will be 0 at the equator. This dip angle can be measured by an instrument known as dip circle. So it is nothing but a compass needle which is free to rotate in a vertical circle. You are familiar with a compass needle. Here a compass needle, you can see here it is placed vertically up. So this needle is free to rotate in a vertical plane. Okay. Now if you are taking this dip circle at the equator, this needle will be directed parallel to the equator. It will be along the horizontal only. But as you move towards the poles, it will be tilted and the tilting will be increasing and it will become maximum, that is 90 degree at the poles. So that is the property of dip. So it is 0 minimum at the equator and maximum at the poles.